All right, so yeah, today we're going to talk about volumes, finding volumes of these solids that are formed by revolving your function or functions about either an axis or a line, but you're basically going to revolve things. And so I'll show you a video of what I'm talking about. And so I couldn't really find what I wanted to find to show you guys this because I wanted to find some sort of like applet type thing that lets you put in a few functions. Here's something else. What else would you be hearing? I don't hear anything. And nothing is happening in my house. Oh, there's a YouTube video playing somewhere. But where? Wait, does everybody else hear that or is that just Mohit? Yeah, Mohit, I think that might be your computer because I don't hear anything. Okay, all right, I was really freaked out. Okay, anyway, no, don't leave. But all right, yeah, so let's look at this example. I kind of forgot what I was saying, but let's look at this example. So I'll try drawing it. Oh, that's what I was saying. I couldn't find an applet. I didn't spend a lot of time finding. I spent like maybe 20 minutes looking and I kind of gave up, but I couldn't find anything that lets you put in functions and then lets you show the video of it revolving, I guess. And so you'll kind of see what I'm talking about in a second when I show you these videos. Actually, you know what? Let me just show you that first. So here, let me go to my laptop screen real quick. So let me show you this video first, and let me turn down the volume on this. I don't think it has volume. But so here they graph the function square root of x, and then, so there's the square root of x, right? But then they are also going to graph a line, so y is equal to 1/10 x. It's kind of slow. It's only a 54-minute or 54-second video, 56 seconds. But so see, if I pause it right now, you guys can kind of see. So then they're going to draw the line x equals 4, which is going to go right here. And so you can see this region, right, is now bounded by these 3 lines. And so I want you to I can't edit this, right? It's a YouTube video, but I want you to pretend or kind of imagine what would happen if instead of having this line right here, this 1/10 x, what would happen if we just had the x-axis right here? If we just put this on the x-axis, right? Then you would have all of this and this piece wouldn't be missing. And so think about what would happen to that piece for the rest of the video if this were on the axis, right? So they color in the region. They're going to take it and revolve it around the x-axis. So do you guys see what just happened? Here, let me go back real quick. And then, so yeah, they revolve it around the x-axis. And now rather than just having a region, there's like that solid piece. And you can find, you don't find areas of solids, you find volumes, right? So we're going to be finding volumes of these things. But what's going to happen, so here, I think they like pull it out of the graph, they pick it up. But yeah, so here, this is what's called a washer, right? So a washer is anything, oh, that was good timing. But a washer, like, I don't know if you guys have heard about it. Like if you go to Lowe's or something, they have washers, right? It's just the things with like holes in the middle as well. What would you have if instead that line was on the x-axis instead of that 1/10 x? Would you still like, what would be different about this piece right here? Yeah, you wouldn't have a hole basically. And so instead of calling it a washer, it's called a disc. And so that's why the title of this section is volumes using discs and washers. And so it's just the difference is when you have a hole in the middle versus when you don't. And so, yeah, so we can keep going here. Let's see what happens next. But yeah, so I was having issues in my last Zoom meeting. So if it's for other people, then I'll end this meeting and we can restart. Because it did that thing in my last class where it disconnected a bunch of times in like 10 minutes. And I just, yeah. And it was telling me my internet was unstable. So I switched internets. But if it's, yeah, so is it lagging for anybody else or is that? All right, so Matthew, try leaving and then joining again. Okay. All right, but so I'm gonna go back to, or here, so I can show you some other stuff. Here's this website that I found. I'll post the link to all of this stuff, but these two right here are just these bottom two links right here. And so there's some other stuff that you can play with. I didn't look at these, to be completely honest, but yeah, so, okay. Oh, shoot. We're not gonna look at the cylinder method, which is the shell method. I think it's the shell method, but yeah, we're not gonna look at that. So disk and washer is what we're gonna be talking about. And so you can revolve it around the x-axis or the y-axis. And so here, this is the function y equals x squared. This isn't as good as that video, but so this is the function y equals x squared. And this is what happens if you loop it around the x-axis or if you revolve it around the x-axis, right? And so you're gonna have, since there's no line right here, you're not gonna have a solid, you're just gonna have like that, the outline or the outside of it, right? You don't, it's not filled in. But then, and so all of ours are gonna be filled in, they're not gonna look like that. But then here, you can also revolve stuff around the y-axis. And so this is 1 minus x squared. And so notice rather than revolving like horizontally, it's revolving vertically. And so that's the only difference between revolving around the y-axis and the x-axis. But so do you guys have any questions about any of these videos that I showed you? Does it kind of help? So try and picture these when we're doing these examples. So yeah, any questions about this? Okay, cool, Matthew. Let me go back to my iPad screen, and yeah, I'll post all the links for that after class. If you want it now, I guess I can post it now. But so here, where is my iPad? There it is. All right. So the first example we're gonna look at is, oh, maybe nothing, there it goes. Y equals the square root of x plus 2. And then the second function is going to be x equals 2 and the x-axis. And so let's draw out the region that's bounded by all three of these things. And so I only need part of the negative x-axis. I don't need the negative y-axis. So x, the square root of x plus 2 is the graph of square root of x shifted 2 units to the left. X equals 2 is the vertical line through x equals 2, and then the x-axis is the x-axis. See if I can draw a straight line. That's not straight, but that's fine. And then this is the region that we are looking at now. And so we're going to take this region and we're going to revolve it around the x-axis. And so it's going to look very similar to the video, the first video that I showed you, except it's not going to have that hole in the middle when you cut a piece out, right? It's just going to be a solid disc. And so, okay, let's write all this out. Part A of this example is find the volume when the region is revolved about the x-axis. And so first, I'm gonna try to draw out, actually no, this one's easy. I'm gonna draw out what it looks like in 2D when you reflect it about the x-axis or revolve it about the x-axis. well, I guess in 2D, revolve and reflect is kind of the same, right? Because you can't really look at it from that third perspective. But so here, you're gonna have, so this is what we started with. So that's just the square root of x plus 2. And then right here, so I actually don't even need that piece. It'll just be this. And then when you revolve it around the x-axis from a 2D perspective, it's gonna look just like you reflected it about the x-axis. And so that's what it looks like from 2D, right? With all of this filled in, so that's all solid. And then, so this is from a 2D perspective. And then let me try and draw out what it would be like from 3D. So from a 3D perspective, I have no idea how this is gonna go. Here, I don't even need the axes anymore. So you're basically gonna have that square root function on both sides, right? And then in here, let's see how this works. You have, it looks like a cup almost, right? And then this, the middle of it, so here, let me use, oh, I guess I should use thicker blue, huh? And then so straight through the middle of this, that's called your axis of revolution. So yeah, you can try drawing these out if you want. 3D pictures are hard though. But yeah, so this would all be filled in, right? Oh shoot, I just threw my pencil. But yeah, so do you guys have any questions so far about what this is gonna look like? Can everybody kind of picture it, right? Oh, you know what? I don't think I should have filled in this portion. I think to be like accurate, you kind of want to leave that separate, right? So like it's still a solid piece, but like this is the outside while the white part is kind of like the inside, I guess. I don't know. Anyway, so the way we're going to do this is we are going to use these things called cross sections. So if you remember back to the video that I was showing, that they like sliced into the whole piece. They just took like a slice out of it and they picked that up and they brought it out of the graph, right? And so that's what we're going to be doing. That's called a cross section. And so here we're going to use cross sections perpendicular to the axis of revolution. Right, so if your axis of revolution is horizontal, your cross sections are going to be vertical. If instead you revolved it about the y-axis, your cross sections are now going to be horizontal, right? Because your axis of revolution is vertical. So these would be your cross sections. And so let's see what that would look like on our 2D graphs. I'm just going to copy all of this and add cross sections to it. And so here, a cross section is basically, from a 2D perspective, just going to look like a thick red line, depending on how like wide your cross section that you pull out is. And you want to make it as small as possible, right? And so essentially what you can do with this, and we're not going to, but what's happening here is the same thing that's happening when you first start learning about integration for areas, right? Because when we first started talking about integration, you had a curve and then you would draw rectangles under that curve. And you would get like an estimate, right? And so those are bad rectangles, but you guys remember that, hopefully. And so you're doing the same thing here. You're taking multiple cross sections out, you're finding the volume of each cross section, and then you're adding them up, right? And so actually, let me show you one more thing. Where is Safari? There it is. So here, if you look, so these two websites that I showed you, if you scroll down, you can see exactly what's happening, right? So here's one cross section, here's another cross section, and they're finding the volumes of this cross section, adding it to the volume of this, adding it to the volume of this, this, and they're getting an approximation. And so it's very similar to what we were doing with areas, but now it's all in the 3D plane, right? And so you can make smaller and smaller cross sections and get a better approximate. And that's exactly what we did when we first started learning about integration for areas, right? And so it's very similar. And so let me go back over here. And so yeah, that's essentially what's happening. And so you want to make your cross sections as small as possible. And we're not going to go through the whole thing again with like the sum and everything and the limit as n goes to infinity. We're not going to worry about that. We're just going to go straight to the integration part this time. So here, oh, hang on. Okay, so yeah, here, this is what our cross section is going to look like. And we're still going to do the same thing that we did in 5.6. We're still going to have top and bottom and everything like that, because when you pull this out, what is this going to look like? What shape is it going to have? So here, let me draw it on the 3D perspective. Yeah, it's gonna be a circle, right? So from a 3D perspective, this is what it looks like, and it would be filled in. Right, so something like that. So if I draw it over here, what it looks like is this, and that would be filled in, right? So yeah. And so we can just find the volume of that by using integration, right? Or we can find the, all right, so if you think about it, when you make these cross sections smaller and smaller and smaller, when you get to the smallest one, you're not gonna have a height, right? And so you're technically, what you can do is you can also find the areas of these things and add those all up to get the volume. And so here, we're just gonna treat this as if it's a flat circle, like a 2D circle, and find the area of it using integration. So you're gonna have that the volume here is the integral from, and so since I'm integrating with respect to x, I need to find my limits, right? Oh, hang on, I forgot to tell you, so the area of a circle is pi r squared, which is gonna come in handy, right? Which is why we needed to know that this was a circle. But so here, what are my limits of integration gonna be? Where does this region start? So think about this as the square root of x plus 2. This is the line, x equals 2. So what's this one? Am I making sense? Let me kind of explain all that again, because I feel like I was a little all over the place. So essentially, what you're doing is you're taking this 3D region and you're cutting it up into like tiny pieces, and you're going to find the areas of all of those pieces. And since those pieces aren't going to have height, you can't find their width, right? So it's just going to have area. And then when you add up all of those areas, like you agree that if you were to take a bunch of pieces of paper, right, think of reams of paper, if you were to take a bunch of pieces of paper and stack them together, you get volume rather than area. And so that's essentially what's happening here, is you're taking a bunch of pieces of paper together and sticking them together to find the volume. And what integration technically is, remember when we first learned about it, you had that the integral f of x dx was equal to the limit as n goes to infinity of a sum, right? Or here, this was 1 to n or something like that, right? And so whenever you think about integration, this is a sum, right? That's why it has an s. It's just like a stretched out s. That's literally what it means. And so when you think about this, what we're going to be doing is we're going to be taking all of the pieces from -2 to +2, all of the flat circles from -2 to +2, and finding their areas, right? And so the area of each one of those circles is given by a pi r squared. But what we're going to need to do is we're going to need to figure out what r is, right? So there is r. That's the radius. So here, that is r. And so if you look at the height from the x-axis, that's a bad color to use there, but from the x-axis up to here, at any given point, what is that radius given by? The square root of x plus 2, right? So here, r is equal to the square root of x plus 2. And so I'm going to be adding up all of the areas, or all of the areas for these circles from -2 to +2. And I'm going to have pi times the radius for any one of those values of x squared dx. And so this is how you're going to find the volume. So this is essentially the sum of the areas of the cross sections. And you get this, here, I'll stop writing in blue. But you get this by looking at, so look at the start and end value on the axis of revolution. Right, so since we're integrating with respect to x, since we revolved about the x-axis, we're going to be integrating with respect to x, which means we need to look at where our graph is bounded on the x-axis. Those are going to be our limits. Oh, I never actually found this integral. But so yeah, here, this is going to be the integral from -2 to +2 of just pi times x plus 2 dx. And then you can just bring that pi out. X plus 2 dx. And then here, this is, so the antiderivative of x is going to be 1/2 x squared. The antiderivative of 2 is going to be 2x, and then you're going to evaluate all of this from 2 to -2. So let's do that real quick. (1/2) times -2 squared plus 2 times -2 minus, so I think this parentheses should go here, minus 1/2 times, oh, I'm doing this out of order, times -2 squared plus 2 times -2. I think I lost track of my parentheses, but that's okay. And so yeah, whatever you get from that. This is 4, so this is 2 plus 4 minus, this is 2 plus -4. So this is 6 minus -2, so this is 8 pi. Are you guys getting the same thing as me? So yeah, let's look at for the next one. Let's go example. Let's find the volume of the region bounded by y equals 1/x x equals 3, x equals 5, and the x-axis, when revolved about the x-axis, or is revolved around the x-axis. Wait a minute. The sentence doesn't make sense grammatically. Find the volume of the region bounded by when revolved around the x-axis. There we go. I think that makes sense. If not, then I'm pretty sure you guys know what I'm trying to say. But so the first thing that you want to do is graph these things. It's just going to make everything a little bit easier, right? So let's graph the 4 things that are going to bound our region this time. And so here, 1 over x is this graph, right? Roughly, it's just a very rough graph of it. But since we're binding it between 3 and 5 on the x-axis, I don't actually need this piece over here, right? But it's there. And so let me redraw this piece. And so here is the positive piece. And then let's say here is x equals 3. And then here's x equals 5. And I know that that is not at all to scale, but that's fine. And so this is not the square root, 1 over x. This is 3, and this is 5. And then you're also binding it with the x-axis, and so this is the region we're looking at. And so when we revolve that about the x-axis, we're going to get this piece now. And so we're gonna do the same thing, right? I'm not gonna draw out the 3D version of this because I'm not entirely sure that I could in a timely manner at least. And so we still know, so when I take cross sections of this, what shape are they gonna have again? Yeah, it's gonna be a circle again. And so we're gonna have the rate or the area of a circle, which is still pi r squared. But what is r now in this case? What is this given by? Yeah, 1 over x for x greater than 0, right? And so when we do this, we're going to have that the volume is the sum of all the areas. And what are my limits going to be on this integral? Yeah, 3 to 5. And so here you're going to have pi times r squared, which is 1 over x, quantity squared with respect to x. And so then you're going to have that you have pi times the antiderivative of, here, let's write it out. Let's go a little bit slower. So this is pi times the integral from 3 to 5 of x to the negative 2 power dx. And so you're going to get pi times, when you integrate, you add 1 to the power. So this is going to be what, negative x to the negative first power? Correct me if I'm wrong there, but I'm pretty sure that's what it's going to be. And you're going to evaluate that from 3 to 5. When you do this, you're going to get negative pi over 5 plus pi over 3, which is equal to 2 pi over 15. So yeah, do you guys have any questions about this example? Okay. So let's do one now where we revolve it about the y-axis instead of the x-axis, and then we can see how our integral is going to change. And so what we're going to be looking at, so example, you're going to find the volume of the solid that results when the region enclosed by y equals x squared, y equals 4, and the x-axis is revolved about the y-axis. Oh, hang on. I don't mean, so I put the region enclosed by the x-axis, but I really mean the y-axis. So the line x equals 0. So I'm going to start drawing this out. So here is y equals x squared. Here is 1, 2, 3, 4. You know what? That is not y. If I'm trying to draw this to scale, it would really be like that. There you go. So this is the region that we're looking at. So let me make it a little bit more obvious. And so now what we're going to do is we're going to take that and revolve it about the y-axis. And so from a 2D perspective, that's just going to look like this. Try not to make it look so triangular. There we go. Right, so there is the solid from a 2D perspective. So since I am revolving it about the y-axis instead of the x-axis, then what are my cross sections going to be with respect to? Are they going to be horizontal or vertical? Yeah, they're going to be horizontal this time. If you tried to take vertical cross sections still, when you pull this shape out, you're not going to get a circle. You're going to get some weird looking thing, right? And so you take cross sections perpendicular to your axis of revolution because that guarantees that it's going to be a circle, right? And so here, I'm going to make a note of that real quick. So note, cross sections are perpendicular. You guys know that means perpendicular. I don't want to write out the word, but cross sections are perpendicular to the axis of revolution because this is how you get circles, or because then they are either discs or washers. We're going to talk about washers on Friday. Okay, so which variable then am I integrating with respect to, x or y? Yeah, we're actually going to integrate with respect to y this time, right? Because if you think about it, I'm going to go back up here. And so when we were integrating with respect to x, where's the pictures? When you're integrating with respect to x, your height is given by y. But when you integrate with respect to y, your height now is given by x, right? All right, wait a minute. Yeah. And so that means that then, yeah, you're integrating with respect to y. And so here, what are our limits gonna be? Oh, actually, before we can write out the integral, that's where I was going with that. Since I'm integrating with respect to y, what is wrong with that? Like if I have my area of integration and I'm given that y is equal to x squared, I can't, I want to have just one variable in here, and it has to be the variable that shows up in like the differential term, right? And so rather than having x squared, what do I want to put right there? Exactly, you're going to have square root of y instead of x squared. And so here, since we are integrating with respect to y, with respect to y, put your equations in terms of y, or in terms of x, technically. Is it in terms of y or x? You want to get x equals y, so yeah, it's going to be in terms of y. And so here you're going to have that x is equal to the square root of y. And then that's really the only thing that we need, right? Because this here is the radius. And so now this is our height, right? And so when you integrate with respect to the variable, the opposite one, not the one that gives you height. And so here, this is going to be r, where r is given to you by the square root of y. And since we're still looking at circles, it's still the area of a circle. So you're going to have the volume. And then now that I'm integrating with respect to y, what are my limits going to be? Where does my region start on the y-axis and where does it stop? Yeah, 0 to 4. Then you're going to have pi times the square root of y squared. And then we're integrating with respect to y. And so this is really just the integral from 0 to 4 of pi y dy. I trust you guys to do that one. When you do this, you get 8 pi. So do you guys have any questions about this section? So far, we haven't done all of this section yet. We haven't talked about washers, which we're gonna save for Friday, because I want you guys to start practicing this first. Do you guys want to do one more example of this? Just to make sure you guys really understand. Well, nobody's saying no, so let's do it. So here, last one. It's pretty simple. Oh, do you want to do one with respect to y or with respect to x? Should we do another y one? Yeah, so let me find an example real quick. Hang on. All right, so let's graph this first. So we're gonna have x cubed plus 2. That's gonna look like the graph of x cubed, but just shifted up 2 units. And so you're gonna have, it's gonna look like this on this side, and it's gonna turn around. And then y equals 4. 1, 2, 3, here's 4. And y equals 8 is somewhere up here. Oops. So we'll just do that for now. The y-axis, and then here. So this is the region that we're looking at this time. And then when you take that and revolve that about the x-axis, you're gonna, or y-axis, I mean, you're gonna get something that looks like that on the other side. And so this is, oh wow, this is 4, and then this is 6. I mean 8. Okay, so then when you take your cross sections, they're gonna be horizontal, and then R is gonna be given by this height or this radius here. And this is given by, again, just this function, so x cubed plus 2, right? So R here is equal to x cubed plus 2. And then remember, since we're integrating, actually, no, it's not x cubed plus 2 because we're integrating with respect to y. With respect to y. And so you need to solve this for y. So you're going to have that y is equal to x cubed plus 2. So x is equal to the cube root of y minus 2. And so that's what your radius is actually given by. So here r equals the cube root of y minus 2. Oh, this integral is going to get messy. We won't actually find it, but so that means your volume then is given by, what are my limits of integration here? Yeah, 4 and 8. And then you're going to have pi r squared. So this is going to be the cube root of y minus 2 squared dy. You can simplify this a little bit. So 4 to 8 pi times y minus 2 to the 2/3 power dy. But then to integrate that, you're going to need u substitution. Do you guys see why? Yeah, right, because you have one function inside of another technically. So I guess we can do it. It's not going to be that bad. But so what you're going to have is, so here, let me bring this over here real quick so I have more room. But so, okay, you're going to have that u should be y minus 2. And then du is going to be just dy, right? So when you go back to integrate this, you're going to have pi times the integral. And so what do I have to do with my limits again? Do you guys remember back to when we were doing substitution and definite integrals? Some of you preferred to just ignore it, but what do I do if I'm not going to ignore it? Yeah, you need to change 4 and 8 to whatever they would be for u. So if I make a yu table, when y is 4, u is 2. When y is 8, u is 6. And so here my limits of integration are now going to be from 2 to 6. And I'm going to have u to the 2/3 power du. And then when you integrate this, you're going to get, so this is going to become 2/3 plus 1. It's 2/3 plus 3/3, so that's 5/3. So you should have 3/5 u to the 5/3 power. And so let's double check that real quick, right? So over here, if I take the derivative with respect to u, I should get u to the 2/3. And so bring the power down. So you're going to get 3/5 times 5/3. U, subtract this by 1, so 5/3. Yeah, you're going to get u to the 2/3. So yeah. And then you're going to evaluate that from 2 to 6. And so whatever that gives you. So 3/5 times 6 to the 5/3 pi minus 3/5 times 2 to the 5/3 times pi. Whatever that is, I don't know. I don't care. So that was actually a pretty good review problem, even though it took 5 minutes to find. Are there any questions about the disk method for finding volumes?